Okay, so I have a list of questions.
Yes. Oh, okay. More people are coming in now. Maybe we should wait for a few minutes or.
Sure.
Okay.
It's okay. Yeah, we can. Yeah. I'm sorry. We have the room for a guest lecture. If you should stay, if you don't mind the voice. So we have a lecture.
Using these two?
The entire classroom for until 6. So it's
But I don't need to leave.
if you don't mind,
Just keep the noise down.
yeah.
But
We have like a Zoom recording.
Got it.
Yeah, let's wait for 3 more minutes.
yeah, sure. Sounds good.
And if there will be something to be written, we might want to change the camera angle when you write it, but that's whatever. Perfect. Yeah.
Jessup always saves the day.
That's great. Thank you.
I heard UChicago ICPC is kind of small.
We are growing. Still in the beginning stage.
It's beginning stage.
I think after Jessup came, our team grew a lot faster.
Oh, really? Really? When was that? How long ago was that?
So previously,
Yeah, it's been around like 3-4 years. Like in the beginning, there's a lot of people when there's like the contests, but the second and third quarters, there tends to be not as many people. So
Yeah.
with the help with Fardan, it's actually better, people showing up than usual.
the midterm, the students,
Right. I think I always feel like, like when I was organizing the club over at Purdue, it was people would show up for like the first 3 weeks, and it'd be like, or even honestly, even like the first semester, because we would just like set up, like really easy contests for the people to do while there, and then like organize events like, oh, let's get into groups and do stuff. But the moment like the actual season starts and then we actually have to practice the actual contests, everyone is like, okay, I don't want to spend 5 hours a week doing a random contest, and then they just leave. So it's just like 2 teams basically at the end.
All right, I'll share over.
I mean, I could.
Yeah, you take this. Me get the door.
I heard you guys got someone new came this year to UChicago, like last name Tron, I think.
Oh yeah, there was a good guy.
Yeah.
He was doing some competitions before.
My friend's friend. I was like, huh, wait, I think I know this person.
Oh, okay. So hi everyone. Today's format will be a 15-minute interview, and then we will walk through a question from 2020 World Finals.
Yes.
And finally, we will have a Q&A session, so post any questions in the chat. Today, joining us to UChicago ICPC is Richard Lee from Purdue University, who got a national 4th place. In which year?
So this would be last year. Not last year, 2 years ago, 2023.
Yes. As you know, regionals is already very competitive, and the national is another level. So, hi, Richard. Would you like to share a little bit? How did you first discover competitive programming, and what motivated you to take it seriously?
Yeah, I mean, I did a little bit of competitive programming back in like high school. Learned about UChicago
Mm.
in 11th grade. I didn't really get super serious into it. But when I came to Purdue, I discovered that there's a bigger community here. There's more people.
Do you guys lecture in online?
Yeah, ICPC.
Is it on Zoom or is it online?
Yeah, feel free to join. It's also in online.
Okay. So we wanted to use the systems that is perfectly fine or that.
It's until 5 to 6.
Yeah. Anyways, yeah, there was just a bigger community over at Purdue, and there was a lot of more people there who were also like kind of really interested in the topic. So I've always liked doing algorithms. I've loved doing math, especially like a math background.
Welcome. Please take a seat.
So
And for the ICPC lecture?
Is it pizza?
Oh yeah, pizza after the lecture.
Oh, yeah.
yeah. So
We have a lot of.
it was just decided to do it just for fun.
That's awesome. Thank you. And in high school, did you participated in any clubs and started training?
So to be honest, our like competitor programming scene in high school is kind of mid. We didn't really have many people interested. Everyone was all into like doing math and stuff. And I think the math background that I got from high school and even like that coming into college where I also did more math really kind of gives me an edge in competitive programming because it's to me it's more basically the same thing. You're just solving problems with kind of like the techniques, the algorithms and stuff you have at hand. And like personally, the way I approach competitive programming is like more of like a proof-based style, like more of like a mechanical style where, I made that kind of way. So I think that type of stuff definitely does help.
That's awesome. And what tools or platform did you use to practice?
Right. So right after I came into college, I really felt like I wanted to take it a little bit more seriously. And luckily there's a ton of tools online that you can find to kind of help you learn algorithms, learn the techniques, like even practice problems, etc. So of course everyone knows about code forces. That's where the biggest contests are held every 2 weeks or so. I haven't done it in a while, but there's also @coder, etc. If you wanted to learn algorithms, there's like UChicago guide, there's CSES, there's CP algorithms, there's CP book, etc., etc. I can like give you guys like a list of all the resources later on, but luckily there's a ton of stuff online nowadays for anyone to really get into it.
Thank you for sharing. And shall we walk through a problem and we can ask some questions along the way.
Yeah,
It
sure.
will be a lot of fun. So I can write out the problem first. It is a ICPC World Finals about 2020.
Mhm.
And it's problem
Math. Yeah. So the reason I chose this problem is so you don't have to write out the full problem statement. I can give like a summary of the problem statement because it's easier.
Yeah.
Again, part of competitive programming is just knowing how to read the problem and extract like the important information out of it.
Right.
But I chose this problem because even you showing people that even at the the highest level of competition, there are still some problems that are totally accessible that you just need a little bit of like ingenuity, and then you'll be able to solve it without any like super complicated data structures or algorithms.
Yeah, I can. Do you want me to write the question a little bit? Or summarize.
Yeah, I mean, we could just summarize it, right? So essentially, we have a bunch of points on a plane. Coordinates are really, really big.
Do you want to? Yeah, be in the main camera. Nice.
Oh, yes. So there's a bunch of points on the grid, and you have a line of a specified width. And the goal is to draw this line like a certain width such that it covers the most amount of points possible. That's basically the problem statement. So
Endpoints?
yeah, n points. And n is less than 3,000. N points less than 3,000. Yes. And also
Line thickness?
yeah, there's some line thickness. You know, it's like 10 to the 9. It doesn't really matter. Thickness.
And what's the problem?
Right. So you have a bunch of points, just endpoints, just dotted everywhere. Right. And you have a line of like a specified thickness, like maybe a line. Yeah.
Go this way.
Would be this thick or something, right? So this would be the thickness of the line. And the goal is to find a orientation of the line such that it covers the most amount of points possible.
So what's the maximum number of points that?
So yeah, what's the maximum number of points that any line of this thickness can cover? And I'll write like right. So the most naive algorithm would just be, okay, so suppose we, actually there's first one observation that we make. So if there's a little bit of like slack in this line, so if you can kind of like think about this line here, I could kind of like jiggle it around a bit and still not have it touch these 2 points, right?
Oh, just a second. Do you have any questions on the
Yeah.
problem statement? Gotcha. That's very well explained.
Yes. So, you know, one thing that you can do is like think about, okay, there's like a little bit of like wiggle room. And so even if I like move this around, suppose like this line always covers this same set of points, right? Even if I move it around a little bit, it's still covering the same set of points. So we can kind of say that even if we move it a little, this line is still the same thing. And we only can't move it when this line, like when it's like constrained on one side by 2 points, essentially. Like if we draw, you know, a line, this line instead, between these 2 points, then we can't really move it around anymore, right? So, but you know, you can still kind of see that they're covering the same points. So we can kind of,
Yeah, can I ask a naive question?
Yes.
I was a little slow. So, if I may, can I use the first example and
yes.
ask a little bit about? So the first example is it is 0, 0, and 2, 4. First point, second point, and also 4, 9,
Yeah,
third
it's just
point.
really high up.
and then 3, 1. 3. So those 4 points. And the idea is to, can you explain the problem?
Right. So what would be the like the thickness? Thickness is 2, right?
Yeah.
So I'm not sure. Would you be able to cover all the points? I think if you draw this line, I'm not sure what this distance would be. If you can't, then the best what is it called? You know, line would be something like this, where it covers 3 of these points, but misses the last one.
Right. The answer is 3.
It's 3. Okay, yeah. So it would, you know, a line of this thickness might only be able to cover these 3 points essentially. So they're not exactly collinear, but because there's like this kind of thickness here, that we're able to cover all 3 points anyways.
That's clear. So, like as a beginner, the initial thought is so the brute force way, is there a brute force way?
Right. So here, right, I'll explain like the initial like brute force way
Okay.
here, right? So the initial thought again is that we can kind of say that every single like possible, like all
possible arrangements are kind of constrained essentially by 2 points here. So in this case, again, if we kind of like move this line all the way over, then once it hits these 2 points, it can't move all the way over. So we can kind of think about it like, okay, if we say, okay, we pick any 2 points and say, okay, then let's check all the points and see whether they fall within a line that's constrained by these 2 points or not.
Oh, so the idea is it to try all of the position of the sixth line and
Essentially,
see
right.
how many points are within each position.
So again, okay, so how many positions and checks do we have to do, right? Because I'm saying here that there could be up to n squared different lines here, right? Because this is covered by each line is essentially constrained by 2 points. If we're checking one line for every 2 points, and we have around n squared different lines. And
That's a good point. Sorry for beginners.
yes,
My proof for thought is to try all the angles, like twist this in a circle, and try all of the degrees.
so
Why is this not necessary?
So this might work, except you also need to like know the position of it as well. And
Oh,
even then, right? How many different degrees are there? Like the question.
Yeah, that would be a lot.
Exactly. So
Floating point.
exactly. So like if you imagine like some really big test case, right? Here we have the coordinates can go up to like 10 to the 9, like plus or minus 10 to the 9. So if like the points are really far away from each other, like the amount of a single little bit of degree change could add a bunch of points or subtract a bunch of points.
Right.
So so this is a good thought, right? And you'll see that actually does end up playing into the solution, but you need to be a little bit more thoughtful about how you do it.
Yeah, so it is trying degree 1, degree 2, degree 3. That was my initial thought.
So again, yeah, try you can try like degree 1, 2, 3, but sometimes maybe like just try like a half a degree can change a lot.
Oh, okay.
Or like a fourth of the degree. And this is a thing with like geometry problems, right? You can't really think super discretely. Maybe the only thing that we can constrain is, again, there's maybe n squared different degrees that we have to try because, we have that many pairs of points.
Yeah.
So now the problem is, if we just try this n squared degrees, what would happen is that because for every single line, we have to check whether every single point is in the line or not, that's a problem because that gives us an n cubed algorithm.
Just to recap, if we fix a position of the stripe,
Yes.
and how to check?
So suppose we fix a position, right? And then we can check whether or not a point is within like the stripe by seeing if it's above this line and below this line, right?
Okay.
So the checking this is again just like math
NQ.
stuff, right?
And
But-
that's the NQ.
Right. So this ends up being n cubed, which is not good because we have up to 3,000 points.
Right.
Which is, n cubed would end up being around like 3 times 10 to the 10, which is too large because, again, the time limit for this problem is 3 seconds, and a good heuristic for the complexity of an algorithm is about 10 to the 8 to 10 to the 9 operations per second. But here again, we were left with a 3 times 10 to the 10 algorithm, which is way higher than what we're allowed. So obviously this algorithm isn't going to work. But what you said earlier actually about the twisting thing is actually pretty good, right? Because if we think about 2 lines that are like kind of close to each other, they're kind of going to cover basically the same amount of points. And so if there's a way to kind of like reuse the calculations, from line to line, then it might be useful, right?
Reuse the calculation.
Right, because again, we're wasting a lot of calculations calculating a bunch of lines that are kind of close to each other.
Right.
Mhm.
Right.
So the trick here is actually to use rotation.
Oh,
But
wow.
of course, the idea is that again, we can't use like discrete intervals. We can't just say, oh, we're going to check every like quarter of a degree,
Right.
because that's not going to work. We still do need to check, for each point. But the idea is, suppose instead of fixing 2 points here, suppose we just fix a single point. And we're going to say the bottom, like this line passes through, this point on like the right side, let's just say. And from this point, we were able to calculate the angle. We can pre-calculate the angle to every other point. So maybe like this angle would be like minus from the horizontal, this angle would be maybe minus 15 or so, minus 10 degrees, and then upwards plus 5, plus 10 degrees, whatever. Okay. And what we can do is, starting off from a horizontal angle, we're going to iterate through all the points in an angular fashion here. Okay. So how does this work? So suppose we start off then with this line that's passing through this point here and this point here. Right. So let me erase these two. Yeah, it's fine. So suppose we start off with, I'll just add some more points up here. With this line, right? So we start off by just counting, okay, how many points are in here? So we have 5 right now.
So this is a stripe.
This is a stripe. And remember, for every point, we're keeping track of the angle it is at, but also, more importantly here, we should also keep track of what angle if we rotate the line upwards, what angle it enters the line, and what angle of the line does it exit the line.
Oh, can you repeat that?
Yeah.
Repeat that?
So again, let's suppose we're taking a look at this point here and this point here. So if we imagine taking this line and then rotating it around this point upwards, then this line at this angle, right? This point enters, this interior area.
Right.
And at this angle, it exits the area as we keep rotating it.
Exactly.
Yeah. So what we can do then is we essentially we're able to just sort these points by angle and, do a rotation of the line around this singular point based on the angles of when it would enter and exit.
Gotcha. So from here to here, we could.
And every single time a point enters the line, we just update the count by 1. And every single time we exit the line, we just subtract the count by 1 of how many points are in the line.
Oh, okay.
Right. So from this, again, then you kind of see how we would kind of accomplish this algorithm, right? So we start at for every single point, we start at the horizontal line. We calculate the enter and exit angles, and then we kind of just rotate around those points.
So for fixed point,
For a fixed point,
we start with a horizontal degree.
yeah, I mean, it doesn't matter where exactly you start. You just start somewhere. You count the number of points in the line. And now, of course, I'm being a little bit loose with just calculate the angle, or just rotate it, right? But again, we can't just check every half a degree or whatever. But what we can do is we know that the only relevant angles here are the ones where a point either enters or exits. So all we have to do is just to sort the points by angle and then iterate through each of those exit and enter angles.
So we rotate and count at every position how many points are within the stripe.
So we keep a running count.
Okay.
Because when the important part is, right, again, when two lines are kind of close and angled to each other, they're going to share most of the points. And again, we only need to check if a point enters or exits the line. We just add one or subtract one,
Oh, yes.
depending on, And so that alone is enough to give us a good algorithm for this problem. Because if we like analyze this algorithm a little bit, so there's endpoints. We're doing this for every point, right? So there's endpoints here. For every single one, we're doing, calculating the angle to every other point, right? And that every other point, there's n of those. And then we might need to sort them like a little bit, right? So we sort them by angle. So we get another log n. So we end up with like an n squared log n algorithm. But that is plenty to solve this problem because log of 3000 is like what? Like 10. So we end up with like a 10 to the 8.
Wow,
And that's enough of the speed up to solve this problem.
that's amazing.
Mhm.
And do you mind walking through this example a little bit? So we start with the horizontal stripe.
Right, we
Here.
start with the horizontal stripe here, okay? And this is 3, 1.
Yep.
Yeah. So initially we have 2 points within this line.
Yes, yes.
Then, okay, so we rotate it up. We check this one.
Okay.
At this angle, this point exits. So this initially has a count of 2. Then we have a count of 1 here after this exits.
Yeah.
Then as this point enters, we have a count of 2 again. Right. So as we rotate this line upwards until this point here enters.
Okay.
Okay. Then we rotate this up even more until this point enters. And we have a count of 3. And then if we rotate it even further, this point exits. We have a count of 2. And then this point exits. We have a count of 1. And so we just take the maximum. On all of
That's
it.
very clear. And those angles are decided by exit and enter for each of the points.
Yes. One other thing is you might also need to check not just like if the point is on the right side, but if we have the opposite side line like this, etc. I think most of the difficulty in a geometry problem is actually the implementation, because with a geometry problem, you're bound to deal with floating point numbers. You have to do like a lot of extra BS to make sure that what is it called? Like that, you can't always like equate to floating point numbers. You have to do a little epsilon, et cetera, et cetera. But it's just, again, this is a world finals problem. This is a problem at the highest level of competition. And it's, maybe the initial thought doesn't work, but if you just think about it a little bit, if you use a little bit of creativity, right, this rotating idea is very nice. You just need to sort the points by angle, and then which angles to check. Like all of these like kind of little ideas add up together, and you get a pretty clean solution.
Just for the detail, when implementing this, we begin with horizontal, and then we find the first point that enters, and then the second point that enters.
So
no exit.
So we sort both the enter and exit points.
Oh, okay.
Like together. It's just that on an entry point we add 1, and on an exit point we subtract 1.
Gotcha. So for each point we have the entry and the exit, and then we sort all of these like to end coordinates. All right, that's super clear.
Yeah. So again, a lot of the implementation detail here is cut out. I think one of the hardest parts is actually implementation. Like, sometimes when you look at a problem and you think of this nice solution and you're like, oh wow, this is such a nice problem. But the key point is like, even though we can think of these, we can kind of like do these problems on paper. A lot of the skill also comes in being able to type quickly. That's a skill that often is forgotten. Personally, I don't type very quickly. I just like doing the math. But that's why ICPC is a team competition and not a solo competition.
Yeah, thank you for sharing, Richard. And finally, a quick 2 question. When doing coding interviews, the hardest type is dynamic programming that you say. But in competitive programming, what is there a type of question that is the hardest?
So first off, if you're doing one good thing, if you're doing competitive programming, is that you never have to worry about an interview ever again because you already know everything. That's, again, dynamic programming, some people have trouble with it, but if you're thinking about it from like a mathematical standpoint, oh, it's just recursion. Oh, it's just induction, right? You can prove these things pretty easily. I think in ICPC, problems are generally divided into like 4 categories. So you have your like typical data structures and algorithms, but you also have your constructive and or implementation. You have geometry and you have math. So math would cover stuff like probability, like combinatorics, like number theory, etc. Geometry would be something like this, where you have points and lines and you have to do a bunch of BS on it. Constructive, if you've ever done code forces, you've probably seen those problems where you have an array and you have to do n operations on an array, and then you have to optimize some value using those n operations. Or it's like kind of like ad hoc problems where you kind of, being able to, simulate the problem and write out things and like correctly is the most difficult. That's like the most important part. Like the hard part isn't about thinking about it, but it's actually about like typing out the code. And the last part is, data structure algorithm, your typical stuff. I think that's the most mechanical. Like you just go online and you learn your data structures, you learn your segment trees and your whatever's, and you just apply them to the problems.
Speaking of the ad hoc problem, so the last question is, any advice on recognizing the patterns among the problem, such as seeing a question and quickly know what algorithm to apply?
I think that comes with practice. That's the only thing. You can be the smartest guy in the world, and if you've never seen something before, it's going to be way harder for you than if someone has done like a similar type of problem like 100 times before. So I think, it's practice, and I think with practice, you kind of learn to see it more. Like as you solve more questions of the same type, you kind of learn, we can apply this, data structure algorithm in this specific way. And then you'll be able to take that onto other problems, so on and so forth.
And do you practice one topic at a time, or just random questions?
I think you need to
start.
You need to be like targeted in your practice, because if you're just like one thing I see a lot of people do is just doing contests, like take 2 hours, do like a past contest, and just keep doing that over and over again. But with that, I don't think you're learning that much, because especially when, under like a contest environment, a lot of it not just goes to thinking, but also like typing it out in implementation, which is an important skill, and you do need to do that to get better. But if you're like just learning algorithms, if you're still like trying to get familiar with new techniques, then actually going like through like a database or archive and practicing problems of a specific type will help you with that type of thinking more.
So choosing a type, maybe for beginners, we can choose one type like graph and then practice.
And I actually think for beginners, it's way easier to get started and to learn, because there's so much to learn, right? Like for data structures and algorithms, again, like
YouTube.
Right. For data structures and algorithms, there's so much that you can like learn as a beginner, even within like maybe like your classes, right? And so there's tons of stuff you can practice. I feel like as you get, to like harder and harder, you start ending up seeing those like kind of same things, but applied in like more intricate ways, like a little bit harder to actually get going. And sometimes the things that you learn will be applicable like one problem in 100, or the techniques that you learn. And so, but for beginners, again, you learn one type of way to solve a problem, and suddenly you can apply to like half of those that the problems that you see, and you get that really nice progress. But I think that's the best part about starting out.
And any questions from the audience? Oh, please.
Like at your level, like legal heights, like when you say like any legal heights compared to like the questions at ICPC final.
LeetCode hards, it depends. Sometimes I will like learn the code, and then a hard I will just be able to like solve because I've seen it before, essentially. But other times, I'll look at it and it's just something completely weird, and I've never seen it. I mean, I think at the end of the day, it's. Do you do code first as well?
No.
No. Okay. But I think legal hearts are like kind of like on like the upper end of like maybe like regionals level, maybe not maybe like middle of regionals level if we're like talking ICPC style contests. And honestly, it's like different too because LeetCode is preparing you for interviews, and the problems are often going to be simpler and more educational and etc. But the problems that you see in contest likely will take more thinking, will take you like, for some of the hard problems, they'll take you like an hour or so of trying to figure out things. And I don't think you generally like see that, on LeetCode if you're already familiar with most of like the main topics. So I think it's like, again, if I had to make a comparison, like about like middle to higher regionals level, but it's not exactly like the same.
Great question.
And also, how long is like the average time it took to solve this? You would estimate.
I don't know. I did not.
The question is, how long does it take to solve a problem like this?
I don't remember. I was there for this World Finals. I did not do this question because I was bad back then. I got along with it because it was like the COVID era, and then a bunch of people got visa issues, and I was like, oh, I'll just hop along. But like for this, I mean, again, the brute force for this algorithm is quite like intuitive and easy to think about. And once you kind of think about this like rotation idea, I think it makes immediate sense, like the way that we implement this, right? Just rotate around, check these specific angles, and keep going. And especially if you've seen other geometry problems, these ideas might come way more easily to you. I mean, maybe I'd say like if I did this problem now, it'd maybe take like 20 to 30 minutes or less to think about like the solution. But then again, with geometry, implementation is the most annoying part, and that all comes with a bunch of details and edge cases and whatnot. So I don't know how quickly I'd be able to do that because I suck at typing, but that's how it is.
I think for me, thinking about the brute force took me 15 minutes. But for the optimized solution, might take like 40 minutes to think of.
Yeah.
And the implementation probably, how long? Is it harder or shorter or longer than the thinking?
I'm going to be honest, I haven't implemented anything in a very, very long time, so I can't tell you how good you should be. But often actually for like a lot of like the harder implementation and geometry problems, you need like an hour to code it. Like if you're solving a problem and you don't have like the solution in the last hour of the contest, you should just give up on it. Because like you're literally writing like 1,000 lines of code for some of those harder problems, and you're like just physical constraints tell you that you cannot solve it past a certain point. So this algorithm is pretty straightforward. You could probably do it in like 20-30 minutes also, or even less if you're more familiar with like the ICPC templates and stuff. But yeah,
Thank you. Any more questions? That's great questions.
I guess I understand the overall strategy of doing, but I guess like how do you use the thickness to get like the like the angles of each point and you're like on this one point? Like how do you know like from the angles that it's in the thickness of the line?
okay. Right.
Great question.
That's a good question. Okay, so you can just do some geometry, right? So suppose we know, like, so this is the point of rotation. We're gonna rotate around this point, and then we're checking, you know, how the line. So the entry line is, sorry, the exit line is easy because that's just like the direct angle, but the entry line is a little bit more complicated. And this is the idea. So when the point enters the line, we can note that if we draw the perpendicular here, we have a right triangle. Right. So we also know the distance between these 2 points. Like this is some distance d, and we also know the thickness t of the line. So just using like arc sine, we can calculate this angle right here. And we just then you know, we also have the angle to, we can also calculate the angle to the like the horizontal in like a similar way. So this would be like this bigger angle would be like alpha. And so the entry angle would just be alpha minus theta. And you know, with like geometry, you end up learning these things, and these things kind of become familiar to you about, and you can kind of intuitively think about, okay, what is a valid operation, what is not a valid operation, what can we calculate quickly. But that all comes with familiarity with, you know, general geometrical concepts and so on. So practice, essentially.
I think we are almost at time. So very good.
I mean, if you have any other questions, like I know you had a bunch of other questions too.
Yeah, the main thing is maybe any advice on how to get started with wanting to get into competitive programming as a first year or second year. I'll start with what platform, Legal first, or is there a book?
I would just recommend just doing Code Forces contests. If you like doing Code Forces contests, then you will like doing competitive programming. That's my take. If you are sitting down at that computer for 2.5 hours and that entire time you're thinking, wow, this really sucks, then maybe, you know, if you really want to grind, then go ahead, but maybe that might not, like, you might not enjoy doing competitive programming as much. And, you know, again, contests are, of course, like really fun. And as a beginner, I think you'll learn a lot just by doing contests because you'll be exposed to a ton of new techniques, but you'll eventually reach like a certain cap. You're like, okay, I'm not improving enough. Then at that point, you just, okay, we need to like figure out what I'm bad at, figure out those problems, those types of problems, and then go and practice those problems specifically. Like every day we'll implement 1 or 2. Try not to look at the editorial, try not to look at the solution until you've thought about the problem for like an hour or 2. And because thinking about the solution part is the most important part. If you already know a solution, you're just typing it out. Sure, that'll help your typing speed, but that might not help the way you think about problems.
Exactly.
And I mean, yeah, after that, it's just you learn more and more, and as you learn more and more, you get better and better, and you do see that improvement. So,
any more questions? Oh, which year are you in?
third,
Third.
yeah.
Let's see. Let's just use the last 2 minutes, and I'll ask one last question, if
Mhm.
that's okay.
Mhm.
So many ask about if they want to pursue a job in AI,
Mhm.
which involves some algorithm. So will practicing competitive programming help them for either AI research or AI industry jobs?
I don't know how much advice I can give on that because I'm not too familiar with like the state of the art stuff, but it is way different. From what I've seen, like if you really want to get into doing like neural network stuff, you should focus like on just studying math. Like
On math.
right, like that's the most important part. Like, you know, understanding like matrices, understanding, you know, all this probability stuff. And understanding like kind of the architecture, and it's really different. I think they're could be some overlap, like in just like the ways you're thinking about things, but I'm not, I'm not on the leading edge of AI research, so I don't really know, how it works. I
Yeah.
can't give that much advice there.
Yeah, like neural network involves some statistics, probabilities. So those kind of algorithms is a little different from this competitive programming algorithm.
Mhm.
Yeah, that's a good idea. But so thank you so much for walking through this question. And for me, I learned a lot. And yeah, and we just want to thank you as UChicago ICPC for Richard Lee to come from Purdue University and give this lecture. Yeah, thank you everyone and have a good day.
Yes. Okay.
Any last word, Jessup?
No, that was incredibly good. I love geometry. We did Convex Hull, I think last year or 2 years ago. Always good to learn about geometry questions. And thank you, Richard, for the wonderful kind of like interview. It was wonderful. I learned a lot.
Mhm. Yeah, no problem. I'm glad to be here.
Perfect. All right.
Mhm.
Thank you.
Thank you. Have a good one.